Hi, everyone. Thank you for tuning into this presentation. So today I am a team member who will be presenting Search-o1. And Search-o1 is Agentic Search Enhanced Large Reasoning Models. So let's see what it's about. So it's about context in reasoning, right? So in recent times, we've seen that reasoning models have popped up. We have the closed source models like OpenAI O1, and even Claude has its own reasoning flow. And the open source models like DeepSeek and Qwen also have reasoning abilities, right? But this reasoning is cut short due to hallucination. So this is where Search-o1 comes in. So it's about context. Let's see. So the deep think mode for reasoning models allow them to deliberate on a problem before coming up with a solution. But these models can run into hallucination or uncertainty. And using standard retrieval-augmented generation does not do much good to this because it adds unnecessary context. So the research gap is large reasoning models run into the risk of hallucination and uncertainty when their knowledge is incomplete. And the solution presented by this paper is it introduces a reason in document approach. So this approach refines extra documents retrieved in an agentic manner, provide the proper extra context the large reasoning model requires to come up with a more complete solution. So let's look at the overview in a very bird eye view. So large reasoning models like O1, Qwen, QWQ, and DeepSeek R1 use reinforcement learning for long step reasoning. And the problem is that they suffer from knowledge insufficiency, and the standard RAG methods fail in stepwise reasoning and also introduces too much context. So Search-o1 reasoning document allows it to dynamically retrieve and refine knowledge. Let's further dive into the challenges. So the challenges is that when it doesn't have enough context, it then starts using uncertain words such as perhaps, likely, alternatively. Like you can see this graph. It used perhaps 30 times per output, right? The outputs of large reasoning models are usually very large before they refine their reasoning and come up with a cleaner solution. So it has so much hallucinations and uncertain words. And the standard RAG approaches brings unnecessary redundant information. So we're trying to go a step higher from standard RAG or retrieval-augmented generation. So let's look at an example. So you can see the system message. The system message is you're a reasoning assistant with the ability to perform web search to help you answer a user's questions accurately. Then the tool we give it in that prompt is that it can perform web search with this begin search query and end search query directives. Then when we get the results from those query, we also inject it into the search results. All right. So the system handles all this. The system handles this part of inserting the search of picking up the search query and doing the web search. Then it brings the results, the refined results into the model. So in this way, the model can continue its reasoning flow with less uncertainties. So this is an example. It's a math problem where we're asking the model to solve this problem, and the problem involves integrating e to the power of x squared. So assuming the model does not know how to do this integration, it then has to get methods of integrating e to the power of x squared. In this way, it produces a better result instead of failing woefully at this maths problem. So the approaches we compared in this paper, or the approaches that this paper compares it to, is the vanilla reasoning, which is like the base, the standard retrieval, where the retrieve documents, where we use standard RAG and just get documents and put it into the reasoning flow, and Search-o1, which is the proposed way where we retrieve documents and refine them. So I'll give it over to Paul to continue the presentation.
Thank you very much, Osinachi. Will you please share the presentation? You can just present with your...
You're up now.
Just a minute. Yeah, it's okay. It's okay. So yeah, so for the next part, we have the experimental setup, whereby we were doing a comparison based on the different data sets. And the data set that we were using, we looked at 4 data sets. One of them was the GPQA. The GPQA is a PhD level science. It has PhD level science questions. We have the second data set, which is the Math 500. The Math 500 has advanced math. It's an advanced math reasoning data set. We also have the live code bench, which provides us with programming challenges. And finally, we use the open domain Q&A, which has general knowledge tasks. And we compared it to different approaches, whereby we had AI without retrieval, which is for the direct reasoning. We had AI using standard RAG. We have also had the AI with agentic RAG, and finally, Search-o1, which is the model that we built. So the graph you can see is for the dataset for evaluation. It shows how O1 consistently outperforms the existing models across multiple datasets. So these are the datasets that we tested, which is the GPQA, the math benchmarks, as well as the live code bench. From science to mathematics to programming, our model delivers quite a higher accuracy compared to the other models, which proves that with smart retrieval strategies, we can get better AI reasoning. So you can see the different benchmarks that we have. And Search-o1, which is the model that we use, has slightly higher accuracies in most cases for the datasets that we use all across the 3 different datasets. Next, let's go to the next page. So for our experimental results, as I mentioned earlier, Search-o1 outperforms all baselines across multiple datasets. And especially in GPQA science question, we had a 5% accuracy improvement. In the math problem reasoning, we had a 10.6% improvement. And in the standard RAG accuracy was around 58.6. And for the Search-o1, our accuracy was 63.6, which was a 5.0% improvement. For the Math 500 direct reasoning, we managed a 75.8%, whereas for Search-o1, we had an 86.4%, which was a quite huge improvement of 10.6%. This shows that better retrieval leads to better performance in terms of reasoning across all the different benchmarks for the datasets that we used. So for the next part, we looked at the performance versus the human experts. In terms of the performance, when we compare them to the human experts, we can see for the GPQA, physicists scored 39.9%, while chemists scored 48.9%, and biologists scored 37.2%. Compared to Search-o1, which is the model we used, it achieved a score of 57.9%, which was significantly higher than all the human experts that were used for this particular benchmark for GPQA. This is actually a breakthrough, which actually shows that these retrieval strategies can actually surpass human experts in terms of reasoning. So in terms of the implementation, on to the next page, we can see that the actual model that we were to use was the Quen 32B for reasoning, but then we decided to move on to the Quen 1.5 to 1.8B chart due to collapse limitation. So this was basically a limitation of space, as well as the resources that we needed to run this model. These models were quite huge, and we could not be able to run them the resources that we had on Colab. So when it comes to retrieval processes, we had Bing Search as the default search API, and due to the API not being the standard API being deprecated, we decided to change the search to DuckDuckGo. So we had to customize our search to ensure that we can be able to use DuckDuckGo, which was actually free, and that was a plus for using DuckDuckGo. And we used DuckDuckGo for the search instead of Bing, and then proceeded to use Gina API to extract and refine relevant information, which was collected from the search. And we integrated all of this to ensure that our AI model can be able to extract this knowledge dynamically, and we were able to get this knowledge into our pipeline, ensuring that our agent can be able to use this knowledge. This was to ensure that Search-o1 can be able to deliver accurate and logical responses. So we also identified some weaknesses. These are potential issues that we needed to address. On to the next page, please. So for the potential issues that we were able to identify for the Search-o1 model, it had quite some limitations. So one of the main limitation was it requires access to such APIs such as Bing or DuckDuckGo. And this means that for you to make the searches, you need to integrate other external libraries or other external search engines to ensure that you can be able to collect information online. The next limitation was it needs documents parsing capabilities such as Gina API, which means that when it comes to parsing the documents that are being collected online, you can't be able to do it with Search-o1 independently. You need to integrate other third parties. These dependencies actually introduce potential points of failure and cost consideration, especially when it comes to Gina API, which is a paid API. And this means that any failure that occurs because of Gina API will be translated back to the Search-o1. Also, another thing is the effectiveness of the approach depends heavily on the quality of the search queries generated. So every single search that is being made by Bing, or if you decide to go with DuckDuckGo, the quality of this search will be transferred directly to Search-o1, which means that if the search was not good, then that will be carried on to the model. Another part is the document analysis by Gina API integration. It adds another computational complexity, which makes the entire application quite resource intensive. And finally, if retrieved information is incorrect, the model may incorporate and amplify these errors. So that was another major weakness, which means that every single search that is being made, if it contains false information, this false information is going to be carried on to our model and might probably not be detected before the model provides you with the final answer. Overall, we came to these conclusions. Please on to the next page. So we came to these conclusions: enhanced reasoning for Search-o1, we concluded that Search-o1 improves large reasoning models by dynamically retrieving and refining external knowledge. Performance boosts in terms of the performance. Search-o1 outperforms standard RAG and direct reasoning across multiple datasets, surpassing even domain experts in some cases. When it comes to the logical flow, Search-o1 ensures retrieved information is relevant, preventing hallucination as well as disruptions. In terms of the challenges that we identified, Search-o1 relies on external APIs, has computational overhead, as well as it depends on query quality. So an improved in query quality will ensure that the Search-o1 provides even better performance in terms of the accuracy. So our future suggestions will be refining the search strategies as well as reducing dependencies, which can further enhance AI-driven reasoning. So thank you for your time. That was the presentation for Search-o1. And we appreciate your time. Thank you.
Yeah, thank you, everyone. We'll stop sharing now.